Hello, welcome back to trigonometry. Today we're going to continue talking about various trig functions, including the tangent and the cotangent functions. So the tangent is the first one we're going to talk about, and then the cotangent is the second one. Okay, so I want to talk a little bit about how we get the graph for the tangent function, and then we're going to talk a little bit from there about how to take the tangent function and do various things to it, such as shifting and stretching and so forth. And then we'll get into the cotangent function the same way. So we'll first talk about the tangent function. Okay, y equals tan x, or f of x equals tan x, gives you your tan function, tangent. Now we learned about the tangent a while back. We learned that the tangent of x is the same thing as sine over cosine. And knowing that, we can kind of look at the unit circle and get an idea about what happens behavior-wise with the tan function. Like if you look closely at the unit circle, just starting over here at 0 degrees or 0 radians, at that value, sine over cosine, you got y over x, or 0 over 1, which is 0. Okay, so at that point, the tan has an x-intercept. Okay, now as we go higher, in the positive, counterclockwise direction, at 30 degrees, or pi over 6, y over x gives us 1/2 over square root of 3 over 2, which simplifies down to square root of 3 over 3. And then we come up here, and the square root of 2 over 2 over itself simplifies to 1. Then we come up here, square root of 3 over 2 over 1/2 simplifies to square root of 3. So what we find is that the values are getting bigger and bigger and bigger. And if you took some of these intermediate values in here that we don't have marked in the circle, the y value is getting bigger while the x value is getting smaller. So y over x keeps getting bigger and bigger and bigger. You're going higher on the circle, but you're going further to the left. So y's are getting bigger, x's are getting smaller. And what happens with fractions when you do that is that you're climbing and getting to really big numbers. Until you get to here, 0, 1. Then all of a sudden you have 1 over 0, which is undefined. So the behavior as you're going this way is that tan is getting bigger until you get to here where it's undefined. Then as you're going this direction, you've got your y's now are getting smaller, your x's are getting smaller. So it's more of a direct variation there. So you start out right here with something that's super small. In here, and then as you're going this way, it's getting bigger until you get to here and here where it's super large. Or it keeps going, excuse me, not quite there. It's getting larger, not super large yet, but it's negatives in here because you have a positive over negative, which is a negative, but it's getting bigger. Here it's 0 over 1, or 0, so another x-intercept. And then now negative over negative is a positive. It's getting bigger. Then here it's super big until you get to this where it's undefined again. And it keeps repeating doing that. You have negative over positive is negative. it's super small. And then as it's getting bigger and bigger and bigger, here you got 0. That's an x-intercept. And then it's getting bigger. Positive over positive is positive until it hits undefined. And you could keep doing that in this circle over and over and over again. But notice that it goes from being undefined here at 3 pi over 2. It gets bigger and bigger and bigger. Starts out right after undefined, starts out teeny tiny. In other words, actually starts out at negative infinity. Gets bigger and bigger and bigger, goes through the x-axis there at 0. Then keeps climbing, getting bigger and bigger and bigger until we get to pi over 2 where it's undefined. And then that whole process starts over again. So from pi over 2 to 3 pi over 2 before it starts over again. Then 3 pi over 2 to pi over 2. Starts over again. The distance of pi. So tan we get is really pi periodic. Unlike sine and cosine that were 2 pi periodic, tan is pi periodic. And at pi over 2 or 3 pi over 2, or at 2 pi, adding and subtracting 2 pi's from those, you'll get places that it's undefined. Okay, so what ends up happening is at those values, you end up on the graph getting something called a vertical asymptote. If it's undefined there, you get a vertical asymptote, which is an invisible vertical line that the graph never touches, never crosses. Alright, let's do a little XY table. Talk about that. For tangent. Like at negative pi over 2, you're undefined. So you get a vertical asymptote. At 0, you get 0. At pi over 2, you're once again undefined. So you get a vertical asymptote. And it continues like that. At pi, you get 0, and so on. Okay, so let's put that on a grid here. Let's mark off. Let's make this pi over 2. Let's make this pi. Let's make this 3 pi over 2. Let's make this 2 pi. Okay, and then go in this direction. Let's make this negative pi over 2. Let's make this negative pi. Let's make this negative 3 pi over 2. Let's make this negative 2 pi. Okay, so at negative pi over 2, place where it was undefined, we have our vertical asymptote. At pi over 2, we have a vertical asymptote. At 3 pi over 2, it's going to be every pi units. So from pi over 2 plus pi, you get to 3 pi over 2. From 3 pi over 2 plus pi, you're going to get 5 pi over 2, and so on. Or going the other direction, at negative pi over 2 minus pi gets you negative pi over 2. Negative pi over 2 minus pi gets you negative 3 pi over 2, and so on. But you get these vertical asymptotes. The graph never crosses or never touches a vertical asymptote. Right, then halfway in between vertical asymptotes at negative pi, when x is negative pi, y is 0. When x is 0, y is 0. When x is pi, y is 0. When x is 2 pi, y is 0. Negative 2 pi, y is 0, and so on. Right, but we really do need some more values. Let's get a couple more. Let's get some in between. Let's look at negative pi over 4. Let's look at negative 3 pi over 4. Let's look at negative pi over 4. Let's look at pi over 4. Let's look at 3 pi over 4. Well, if you do a tangent of negative 3 pi over 4, then you go in this direction, right? Negative 3 pi over 4 puts you there, and you get negative square root of 2 over 2 over negative square root of 2 over 2, which is just going to give you 1. If you look at negative pi over 4, that puts you here. Negative square root of 2 over 2 over square root of 2 over 2 is going to give you negative 1. Pi over 4, so these two positives, same thing, going to give you positive 1. And then 3 pi over 4, this over this is going to give you negative 1. Okay, so that gives you some more values that you can fill in on your graph. So let's see here. Let's mark it off as, let's make that 1. Let's make that negative 1. So for this value here, we're going to have 1. For this value here, we're going to have negative 1. This value here, we're going to have 1. This value here, we're going to have negative 1, excuse me. Erase that. For this value here, we're going to have positive 1. This value here will have negative 1. Here we'll have positive 1. Here we'll have negative 1. So on. Now what's happening is, like, from the x-intercept up that way, it gradually climbs in a curvy kind of way. And then going to the left, it gradually declines in a curvy kind of way. It does that for all of these. And it just keeps repeating over and over and over again. So, a little bit more about this. The domain for this is all reals except odd multiples of pi over 2. The range is all reals. This is an odd function. You look at it, it has origin symmetry. And being an odd function means that tan of negative x equals negative tan x. So if you look at the graph again, you can take this part, rotate it around, it matches up with this part. Or tan of positive pi over 4 gives you positive 1, while tan of negative pi over 4 gives you negative 1. So there's that. Period is pi. Okay, so that's a little bit about the tan x graph. Okay, now let's go into more depth and start taking this tan x graph and manipulating it. What if we have some variations of tan x. Just like with sine and cosine, we can have shifts and stretches and all that good stuff, you know, translations, etc. For y equals tan x, you have two consecutive asymptotes. At x equals negative pi over 2 and x equals pi over 2. That's pi periodic. That's pi periodic. Okay, so in this case we can take negative pi over 2 and set that less than bx minus c and set that less than positive pi over 2. There's going to be an x-intercept. Midway between consecutive asymptotes, consecutive vertical asymptotes. So 1/4 and 3/4 of way. The y coordinates are at negative a and a. Alright, so let's say we have to graph y equals 3 tan x. Tan 2x, excuse me. And we're going to graph this over negative pi over 4 is less than x, which is less than 3 pi over 4. Alright, first for the asymptotes. We can take negative pi over 2, which is less than 2x, which is less than pi over 2. Solve that. You're going to get negative pi over 4, which is less than x, which is less than pi over 4. And then you can also repeat. Then the x-intercept is going to be at 0, 0. And then you're going to have at negative pi over 8, comma, negative 3, and positive pi over 8, comma, positive 3. Okay, so for that one, let's do a graph on that. We'll put negative pi over 4 here. So positive pi over 4. This is pi over 2. This is 3 pi over 4. Alright, so negative pi over 4 and pi over 4 are going to be vertical asymptotes. Then it's pi periodic, or it's periodic, so if it's from negative pi over 4 to pi over 4, we've got a period of pi there. So then over to 3 pi over 4, we're going to have more vertical asymptotes. Alright. Then x-intercept at 0, 0. But then we'll also have an x-intercept here. So notice it's halfway between this one and this one. We got this. Halfway between this one and this one, we got this. Then negative pi over 8, negative 3. Whoops. Negative pi over 8, negative 3. Ooh, I need to mark that off. Alright, let's do... Okay, we'll just do our usual... 2... No, you know what? I don't want to do that. I want to do... that. What did I use on this one? I did use that, but... Yeah... I'm going to have to do this. I'm going to have to go 1, 2, 3, and then I'm going to have to go negative 1, negative 2, negative 3. Okay, negative pi over 8, negative 3. So that puts us here. Positive pi over 8, positive 3 puts us here. And then repeat. Repeat. And connect with a nice smooth kind of curve. So there's your graph. Notice that it was vertically stretched by a factor of 3. As you can see in the A part, right here. So that part vertically stretched by a factor of 3. And then this part caused a horizontal shrink, horizontal squish. When you look at the graph. Okay, let's do one more. Let's do y equals tan of x minus pi over 2. This should cause a bit of a shift. Because you have the pi over 2 being subtracted from x. And so we learned about that, making it, it's going to shift right pi over 2 units. That's what that's going to do. Okay, but then for the asymptotes, all right, we can take negative pi over 2 is less than x minus pi over 2, which is less than pi over 2. Take care of that, you end up with 0 is less than x, which is less than pi. That'll help you with your vertical asymptotes. And then x equals pi over 2 will give you x-intercept. So at 0 we're undefined. At pi we're undefined. Halfway in between pi over 2 we have our x-intercept. And we got at pi over 4 we should get negative 1. And at 3 pi over 4 we should get positive 1 because a is 1. Alright, so let's go ahead and graph that on the grid. Okay, in this case, let's do let that be pi over 2. There's pi. There's 3 pi over 2. There's 2 pi. And then we'll go ahead and let it be 1, 2, and then -1, -2. Alright, so we're going to have a vertical asymptote on the x-axis at 0. X equals 0. We're going to have another vertical asymptote at pi over 2. Or no, not pi over 2, excuse me. At pi. Another one at 2 pi. It didn't come out very well. It's 2 pi. Okay. Then we had x-intercept at pi over 2, which means we should also have one at 3 pi over 2. And then at pi over 4 we had -1. At 3 pi over 4 we had +1. And then that repeats here. And then we can just connect with a nice smooth curve. Okay, let me show you how that's going to look on the calculator before we move on to cotangent. Let's look at this one we just did. Let's do it on the calculator. Let's see, my mode right now is in radians. Okay, so then let me go to y equals, and let's graph this tan of oops, sorry. Go to y equals, let's graph this tan of x minus pi divided by 2. Say graph. Let's just see what happens. And there you go. There's the beautiful graph. And you can zoom out and see more, or you can zoom in and see less, but you got 0 here, you got the pi here, you got the 2 pi over here, and then right here you got at pi over 2 you got an x-intercept, at 3 pi over 2 you have an x-intercept. Let's see, if we go to table, then we can see at 0, error, that's one of the asymptotes. Let me see, let me start this. Let me go to table set. Let me start it at 0, and let's do increments of pi divided by 8. Let's see what we get. Alright, so then you can see what's happening there. There's the -1, there's the 0, there's the 1, then there's pi. And it keeps repeating over and over again. You can see basically what's happening there. Okay, so that's tangent. Let's talk about cotangent next. Now cotangent goes well here because it is it's reciprocal of tangent. Okay, just like tangent, the period's going to be pi. But let's do a little table and think about what's happening here. Right? If x is 0, tangent is 0, the cotangent is going to be 1 over 0, which is undefined. If x is pi over 6, tangent is square root of 3 over 3. cotangent's going to be square root of 3. If x is pi over 4, tangent's 1, cotangent's 1. If x is pi over 3, tangent square root of 3, cotangent is square root of 3 over 3. It's always the reciprocal. And so on. And when you get down to pi over 2, pi over 2 and tangent is undefined, but on cotangent is 0. 3 pi over 4, tangent is negative 1, cotangent's negative 1. At pi, tangent 0, cotangent's undefined. What you end up getting with this reciprocal function is something that looks a lot like it looks like the tangent function reflected and shifted. That's what ends up happening. You end up with the period of pi, but here the domain we can say is all reals except integral multiples of pi. And that's where our vertical asymptotes come in. Still halfway in between vertical asymptotes, you're going to have x-intercepts. It's still odd. Still has origin symmetry. It's just that the vertical asymptotes are shifted from the tan ones. Tan's at 0. Tan has a x-intercept at 0. Cotan has a vertical asymptote there. Tan is undefined, has a vertical asymptote at pi over 2. Cotan has an x-intercept there. And what happens too is like pi over 6 for tan is smaller, while for cotan it's larger. Pi over 3 is larger for tan, smaller for cotan. So like while tan here is climbing, getting larger and larger, cotan is going down, getting smaller and smaller. So it's like you have the same kinds of curves reflected and shifted when you get to cotan. Right, so let's see here. Let's mark this out. Let's mark out 1, 2, 3, 4. Put pi here. 1, 2, 3, 4. Put 2 pi here. Knock it off. 1, 2, negative 1, negative 2. So with cotan, we have a vertical asymptote here. We're going to have a vertical asymptote here, and a vertical asymptote here. Then our points, whoops, our points, we had x-intercepts halfway between. And then halfway between a vertical asymptote and the x-intercept, on this side you're going to be at negative a, that side you're going to be at positive a. Negative a. Oh, sorry. I keep thinking about looking at the wrong thing. I apologize. It's reversed from tan. It's switched from tan. This side you're going to have positive 1. This side you're going to have negative 1. This side you're going to have positive 1. This side you're going to have negative 1. So then when you connect the dots, the curve looks a lot like the tan curve. Forgive my drawing here. Woo. But it looks like it's reflected. Alright, I think even better, let's put it in the calculator. It'd be even easier to see there. Like we had y equals, let's just do tan x here. And then go on down and let's do 1 over tan x. And then let's make that one a little thicker. Why won't it go over? It's supposed to be able to go over here and make it bigger. Why is it not cooperating? It's like it froze up on me or something. Alright, let's try that again. I must have been pushing the button too many times. Alright. Let me see here. I'm going to see about getting this refreshed. Oh, it won't even close. It's really tied up. Okay. Well, now maybe it's closing. I don't know. Okay, I had to go run a little task manager and start it and quit the program and start it over. So let's start fresh here. Y equals tan x, and then we'll go down. Y equals 1 divided by tan x, and then we'll carefully scroll over, hit enter just to make that one thicker, and then hit graph. So you're seeing it graph tan x, and then next you're going to see it graph cotan x, and you can see the relationship between them. So tan x, you had your vertical, where you had the vertical asymptotes for tan x, you have x-intercepts for cotan. Where you had x-intercepts for tan, you have vertical asymptotes for cotan. Cotan's sloping down, it's decreasing over its intervals, while tan is increasing over its intervals. So you can see the relationship there between those. Alright, let's graph one more cotan, just to make sure we've seen enough of those. Let's talk about, cotan when you have more going on, like y equals a cotan bx minus c. So we do 0 is less than bx minus c, which is less than pi for the asymptotes. So if you have like y equals 1/2 cotan of pi over 2x, 0 is less than pi over 2x, which is less than pi. So 0 is less than x, which is less than 2. Let's see, and here the a is 1/2. So that tells us it's going to be vertically squashed. You're going to have an x-intercept halfway in between at 1, 0. Like if you have 0, 2, 1, that's going to be an x-intercept. And then at 1/2, you're going to have and at 3/4 or 3/2, excuse me. Alright. So let's put that on a grid. Look at it. There's 1. There's 2. There's 3. There's -1. There's -2. There's -3. Alright, so at 0 we have an vertical asymptote. We have the x being undefined there, making it undefined. X equals 0. Cotan's undefined. At 2, another vertical asymptote. At -2, another vertical asymptote. We have intercepts at 1, 3, -1, -3. we found out that at 1/2, we're going to have 1/2. At 3/2, we're going to have negative 1/2. 1/2, let's see, I got to mark this off now, don't I? Let's make that 1. Let's make that negative 1. 2. Negative 2. Alright, so at 1/2, we have 1/2. At 3/4, we have negative 1/2. And when you connect, this nice curve like this. And there you go. So you had the vertical squash. It's like it's being squashed down. But then you also have this right here causes the horizontal stretch kind of action. Stretching, shrinking kind of action. Like normally cotan would be only pi wide, but now it's like only 2 wide. So in this case it ends up being a horizontal shrink kind of action. Because instead of the asymptote being over here at pi at 3.14, it's at 2. But you know, we can put that on your calculator as well and just kind of compare and see what's happening. Let's see, let's do 1/2. Actually, let's clear that. Let's do 1/2 or 0.5, and then 1 divided by tan of pi over 2x. Let's try graphing that, see what happens here. Helps you to compare. So the black one was the original cotan graph, and then the thick black one, and the thin black one is the new one, the 1/2 cotan pi over 2. So you can see where the thin black is not only narrower, but also like seems to start going starts taking off at a different rate than the thicker black one. So they have their effects with having the A and the B in there. Alright, so there you go. So there's a little bit about tan, a little bit about cotan. So now you can have your hand at trying to graph these and practice in your homework. But there's the basics about them. Be sure to join us because we still have 2 other reciprocal functions we haven't talked about, cosecant and secant, and that'll be in the next recording. I look forward to seeing you then.